Hey everyone, and welcome to today's Explainer. I am super excited to have you here because today we are taking a deep dive into section 6.2 of our source material, and we're focusing entirely on this totally fascinating intersection where pure physics crashes right into human biology. We're talking about the science of loudness. Now, it's a phenomenon that bridges acoustics, the objective physical behavior of sound waves in the air, and psychoacoustics, which is how our nervous system actually interprets those waves. We experience it every single day, right? But the way our brain processes loudness is wonderfully complex, mathematically intricate, and honestly, way more deceptive than you probably think. So let's kick things off with a mystery most of us have run into. Picture this. You're listening to your favorite music, you reach over to the volume dial on your amp, and you absolutely crank it. The physical energy, the actual literal wattage pumping out of those speakers, doubles, or maybe even triples. But to your ears, it barely moves the needle. It definitely doesn't sound twice as loud. Hooking into this everyday reality is kind of the perfect way to understand that the physical volume dial just does not match our biological ears. But why the heck is that? Well, let's get into our first major concept. What is loudness? To really answer that question, we need a complete paradigm shift. We have to establish the fundamental difference between what a sound physically is in the real world and how we actually experience it inside our heads. The crucial thing here is drawing a stark contrast between two very different concepts. Over on one side, we have physical magnitude. This is your sound pressure, your intensity, your raw power. These are objective reality that you can measure with a microphone in units like decibels. But on the other side, we have subjective magnitude, and that is loudness. Loudness isn't floating around in the air. It actually requires a nervous system to interpret it. It happens entirely in our minds. So when you turn up an amplifier to increase the physical intensity, what you are perceiving is a change in loudness. Let's lock in the actual definition here. Loudness is defined as the perceptual quantity most related to sound intensity, literally the subjective magnitude of the sound. Because of this, it's actually scientifically inaccurate to say, hey, this sound has a loudness of 50 dB. Decibels are strictly a unit of physical magnitude. You simply cannot measure a feeling with a decibel meter. Now, sure, people mix the two up all the time because sound pressure and loudness do scale together perfectly at certain mid-frequencies, so it's easy to use them interchangeably in casual conversation, but for acoustic engineers, they have to keep them strictly separated because outside of that narrow frequency band, the correlation totally breaks down. Moving right along to section 2, the loudness matching technique. Okay, so if loudness is entirely a subjective feeling, like a biological illusion, how on earth do scientists measure it? Well, they use equal loudness contours, mapping pure tones to a 1000 Hz reference tone to solve that exact problem. Instead of trying to measure the feeling directly, scientists play a reference tone and just ask a listener to adjust the volume of another tone until it magically feels just as loud. Now check out the bottom curve we're looking at. That represents the minimum audible field, basically our absolute threshold of hearing. Notice how our ears are incredibly sensitive in that middle 1000 to 6000 Hz range? That's not an accident. It's an evolutionary adaptation tuned perfectly to human speech. And because of this tuning, we need way more physical acoustic power at low frequencies just to get the same mental perception of volume as we do for a mid-frequency tone. To keep all this organized, scientists created a whole new vocabulary. Enter the phone. A phone is our baseline. It's a unit of loudness level equal to the level, in decibels, of an equally loud 1000 Hz pure tone. So if a random sound feels just as loud to you as a 1000 Hz tone played at 60 decibels, we say that sound has a loudness level of 60 phones. And phones are absolutely crucial in the real world. They provide a unified human baseline for matching subjective volume across any frequency, which is exactly how we calibrate audio equipment or design effective hearing aids. But here's the kicker. Loudness matching isn't just about frequency. It applies to bandwidth too. As the bandwidth widens, a really surprising truth is revealed. If you take a sound and spread its power over a wider bandwidth, the perceived loudness actually goes up, even if the overall physical intensity stays exactly the same. This introduces a huge concept called the critical band. See, the basilar membrane inside your ear acts like a bank of bandpass filters. When a sound is narrow, it hits just one filter. But once that noise widens and exceeds the ear's critical band, the acoustic energy spills over into adjacent auditory filters. And that spillover, it causes your brain to perceive a sudden distinct jump in loudness, even though there's zero increase in actual physical energy. Crazy, right? So let's quickly summarize the 3 major ways our biological filters mess with sound. First up, frequency sensitivity. Our evolutionary bias towards speech means we naturally hear mid-range tones much louder than very low or high ones. Second, bandwidth spread. Thanks to that critical band mechanism we just talked about, distributing sound energy across multiple cochlear filters tricks our brain into hearing it louder. And third, we have duration. This introduces temporal integration. Your ear actually acts a lot like a camera, accumulating light, integrating sound energy over a specific window of about 200 milliseconds. Because of this, a tiny, short 10-millisecond tone needs drastically more physical intensity to match the perceived loudness of a continuous 200-millisecond tone. Loudness isn't just pure level, it's heavily dependent on how sound is distributed over time and frequency. Now let's dive into the math with understanding loudness scales. Okay, so we know how to match loudness, but how does it actually scale as it gets louder? To figure this out, researchers use two tests, magnitude estimation and magnitude production. In magnitude estimation, you listen to two sounds and literally just guess a number for how much louder one feels compared to the other. In magnitude production, you tweak a dial until the sound feels exactly twice as loud. As you can imagine, these psychophysical tests are notoriously difficult. We are heavily biased when assigning arbitrary numbers to our feelings, which is exactly why scientists need massive sample sizes to average out our individual quirks and lock down a mathematically reliable baseline. And the culmination of all those rigorous experiments? Stevens' power law. It states that our subjective sensation, loudness represented by L, scales with the power of the physical magnitude, which is intensity represented by I. To put a number on this feeling, scientists use a unit called sones. One sone is the loudness of a 1000 Hz tone at 40 decibels. Now, in this equation, the constant K just depends on your units, but the real star of the show is the exponent, alpha. For most normal sound levels, this exponent dictates how compressed our hearing is, and it's actually quite small, usually sitting right around 0.2 to 0.3. And because that alpha exponent is so tiny, we get a massive aha moment. Loudness is a severely compressed version of physical intensity. If you want a sound to feel just twice as loud to your brain, you cannot just double the physical intensity. No way. You actually have to increase the physical intensity by a factor of 10. This is a massive rule of thumb for audio engineers. A 10-fold increase in acoustic power equals a 10-decibel increase in sound pressure, which finally gives you exactly a 2-fold increase in perceived loudness. So going back to the start of our explainer, if you want your new guitar amp to sound twice as loud as your old 10-watt amp, you literally have to go buy a 100-watt amplifier. Let's ground this visually. Look at this curve showing loudness in sones against sound level in decibels. See how it bends? It's steepest at the lowest levels, and then it dramatically compresses. This abstract math perfectly matches the mechanical biology inside your cochlea, specifically your outer hair cells. These little cells are brilliant. They act as nonlinear active amplifiers. When it's super quiet, they actively amplify sound so you can hear a pin drop. But when it's loud, they dynamically compress the mechanical vibration. This compression is a lifesaver. It protects your delicate inner ear and radically expands your dynamic range, letting you handle the roar of a jet engine without completely overwhelming your sensory system. Let's bring this all together in our final section, models of ear loudness. To truly map out how we hear, we have to look at specific loudness and excitation patterns. Specific loudness is basically the area of excitation spread out along your uncoiled basilar membrane. It perfectly mirrors the tonotopic map of your ear, where highs hit the base of the cochlea and lows hit the apex. When a complex sound enters your ear, it activates a distinct pattern across multiple localized filters. And because of that biological compression from the outer hair cells we just talked about, spreading the energy across the map means each individual filter doesn't get compressed as much. This physically reinforces why wider bandwidths sound louder to us. Which brings us to the ultimate conclusion. Total loudness is simply the sum of all the specific neural activity across the basilar membrane. Think about it. Your ear takes a physical sound wave, chops it up into different frequency bands, mechanically compresses the energy at each specific point, and fires those neural spikes right into your brain. And then, your brain performs an instantaneous act of real-time calculus. It integrates the total area under that excitation curve across every single frequency. The result of that wildly complex math is just that one seamless feeling you call loudness. So what's the big takeaway here? Loudness isn't just a physical volume dial at all. From the invisible physics of sound waves, to the nonlinear compression of your hair cells, right down to the real-time neural calculus in your auditory cortex, loudness is an absolute masterclass in biological engineering. It is a highly engineered, deeply subjective illusion designed purely to help you safely navigate the physical world. Your brain isn't passively recording. It's actively interpreting, compressing, and mathematically summing energy to literally construct your reality. It makes you wonder, if just turning up a volume dial is this biologically complex, what else is your brain seamlessly remixing for you right now? Thank you so much for joining me on this explainer. I really hope you walk away with a brand new appreciation for your own incredible ears. Catch you next time.